Hello, welcome to Maths with EJD. We're still talking about spectral analysis, and this is the second video where our focus shifts to the mathematical and physical background of spectral analysis. All right. Of course, I have a newfound love for Google Colab these days. So I get to do everything in that environment because I can easily write my codes, write my text, code equations, and all of that here. So we are going for the second topic here, and that's talking about the physical and mathematical background of spectral analysis. That's what we have right here. Okay. So um now we have an introduction to that idea. Spectral analysis, of course, provides a powerful framework for understanding and representing signals in terms of their frequency content. Okay, so to appreciate its principles, one must first understand the mathematical and physical foundations upon which it is built. Okay, so basically, spectral analysis is built on mathematics and physics. That's what we are saying. So this section introduces essential concepts such as sinusoids and harmonics, the superposition principle, basic trigonometry, and Euler's formula, the role of complex numbers in frequency analysis, and the physical interpretation of frequency, amplitude, and phase. Okay, so let's move ahead to talk about sinusoids and the superposition, sinusoids, harmonics, and the superposition principle. First of all, we talk about sinusoids. Basically, sinusoids are just sine and cosine waves, right? And they are the building blocks of spectral analysis. And that is why this is Fourier series is really integral to the whole idea of spectral analysis because Fourier series helps to transform data in the time domain into data in the frequency domain into sinusoids, basically. So any periodic signal can be represented as a sum of sinusoids with different frequencies, amplitudes, and phases, a principle formalized by Fourier analysis. So you see that a sinusoid is a smooth periodic oscillation described as x of t equals a sine omega t plus phi. So here A is the amplitude. It tells us how high or how low the wave can go. And then you have omega, which is the same thing as 2 pi f, 2 pi times frequency, which is the angular frequency. And then you have the frequency itself, which is the frequency in hertz. And you have phi, which is the phase, right? So phase is like how one wave is leading another if you have more than one phase or something like that. Okay. Then you come up to the idea of harmonics. Harmonics simply refer to sinusoidal components whose frequencies are integer multiples of a fundamental frequency. So you have a fundamental frequency, and then you have harmonics, which are integer multiples of that fundamental frequency. Those are actually called harmonics. They are sinusoidal components whose frequencies are integer multiples of a fundamental frequency. Now, these harmonics, they shape the overall waveform, determining its complexity and timbre in applications like acoustics, right? So for a periodic signal with fundamental frequency f naught, for instance, harmonics are integer multiples. So if you have f naught as the fundamental frequency, so your harmonics are actually fn, which is equal to an integer value n multiplied by the fundamental frequency. So if you have f naught, then it means f naught, 2f naught, 3f naught, 4f naught, and so on and so forth are actually harmonics in that regard. Okay, then we have something we call the pure tone. The pure tone is the only fundamental frequency, that's your f naught. But when you come to things like musical instruments, right, you can have the fundamental frequency plus many harmonics. That is why you have where you have musical instruments coming into the whole thing. Now, let's talk about the superposition principle. The superposition principle, which is the cornerstone of linear systems, states that the response to a sum of inputs, okay, the response to a sum of inputs equals the sum of the responses to each input individually. So the response to a sum of inputs equals the sum of the responses to each input individually. Now that may look somewhat bogus, but the mathematics behind it is going to make it a bit clearer. So this principle enables decomposition. So you can decompose, right? And the reconstruction of signals from their frequency components without loss of information. In linear systems, the total response equals the sum of individual responses. So if you take a response, and if you take several responses, like from here now you have x of t, is equal to summation from n equals minus infinity to infinity. So every possibility you can have in the from for over the whole real number system, right? So from minus infinity to infinity, let's assume you're starting from, let's even take it from 0 to infinity, for instance. So it means you have n to be 0 now. So that'll be c naught e raised power j times 0. So that'll be, so it will just be c naught, right? Next to be c1 e raised power j omega naught t, and then c2 e raised power j2 omega naught t, and so on and so forth, right? That's the idea of so you have each of them, and then by the time you sum them up, that's why you have this whole summation. So the superposition principle allows decomposition and reconstruction of signals. So you can decompose signals and reconstruct them. That is the whole idea of superposition. Now, let's see another foundation. We are talking about the mathematical and physical background of spectral analysis, right? So let's talk about basic trigonometry and Euler's formula. Okay, these are very fundamental things, that are building blocks for spectral analysis. So talking about trigonometric identities, for instance, trigonometric functions, particularly sine and cosine, describe oscillatory behavior in the time domain. So key trigonometric identities used in spectral analysis are things like sine squared theta plus cos squared theta is equal to 1. So, I mean, this simple expression, you can use it to prove the Pythagoras theorem, and you can use it for so many, you can use it to derive other trigonometric relationships like that, as simple as that looks. And then you have cos A plus B equals cos A cos B minus sine A sine B. So these identities help in manipulating sinusoidal signals, combining or decomposing them, and understanding their orthogonality, right? So trigonometric identities actually are very helpful. So you can visit, I have a whole playlist on trigonometry. So you can check the playlist out to see the trigonometric identities. Of course, what you can just do is you can just go to YouTube. So from YouTube, you can see, I think, to see all these playlists that I've been mentioning, in case that may not be easy to find for you. So just click, well, I mean, this is me on my channel, so it may not be the same. But once you get here, just click on playlists. And once you have click on playlists like this, you can find all these playlists I've been talking about. So I'm still working on Python basics. So I'll be working with dealing with that side by side spectral analysis. Then I think I've talked about trigonometry. It's one of the earliest playlists I ever made. Yeah, I think it was the third. Where is it now? Okay, complex numbers. Yeah, trigonometry. I have 10 videos on that. So if you check that out, you're going to see trigonometric identities and things like that I'm mentioning now. So that can actually help to clarify some of the concepts I am discussing. Okay. Then of course I've also talked about, what else have I talked about? Yeah, trigonometry. I've talked about Fourier series. So the playlist on Fourier series, I think it's up some, yeah, after binomial series. Fourier, I have binomial series, I have Fourier series, and so on and so forth. So it's better if you click on playlist, you can find this playlist and then follow up with those things. Okay, so back here, I talk about Euler's formula. Euler's formula connects complex exponentials and trigonometric functions. So Euler's formula helps to simplify. So now, trigonometry can be quite bulky, especially if you check if you are interested in complex numbers, for instance, you'll discover that there are some points that things become so complicated in complex numbers that we now need to use Euler's formula to make them really easier, right? And that's where we talk about polar forms of complex numbers. So we can use exponents to represent trig and make things a bit tidier, right? So Euler's formula connects complex exponentials and trigonometric functions. Like you have e raised power j theta equals cos theta plus j sine theta, basically. So you see this simple thing represent this whole thing. And sometimes it's easier to work with this to make things pretty easy. So this simplifies sinusoidal representation. For instance, you have a cos omega t plus phi. So since we are dealing with cos here, you already know that the real part of this kind of expression is cos, while the imaginary part is sine. So that's why we say we take the real part of a e raised power j omega t plus phi. So whatever you get, just take the real part. And that, of course, that's sure to be the cosine component of that expression. Okay. So Euler's formula makes calculations of phase, amplitude, and rotations in the frequency domain easier and more intuitive. So Euler makes things pretty direct and all that. Okay, then we come to the idea of complex number. You can say I've talked about trig, I've talked about complex numbers, I've talked about exponentials, dealing with Euler's, right? So Euler's number. So complex numbers and frequency analysis now. So first of all, complex numbers extend real numbers with an imaginary unit. So you're dealing with numbers generally, and then once you have this, you have to talk about the square root of -1. Then that is what introduces the whole idea of complex numbers. And generally, complex numbers are written as I think I want to split this up. Let me see. I want to split this up, right? Okay, I'll just copy and paste this, and then just delete sequentially. This can come, and then I have this gone. Okay, so it can all be separate. So you can really get the gist. You can get the gist better than what it was before. Okay, now I have it split up. Now, complex numbers extend real numbers with an imaginary unit. So once you introduce just this j, which is the square root of -1, of course, that comes from the idea that j squared is equal to -1. So j is square root of -1. So z is x plus j y. So j is square root of -1. That brings us to the whole idea of complex numbers. So this enabling a two-dimensional representation of oscillations, amplitude, and phase on the complex plane. So you can have an imaginary part and a real part. The real part is x, the imaginary part is y, which has a j attached to it. Okay. Then you talk about sinusoids in complex form. So, we talked about sinusoids. That's one of the first things we talked about. They are basically sine and cosine waves based like that. So in frequency analysis, a sinusoid can be represented as x of t equals ae raised to power j into omega t plus phi, where a is the amplitude, omega is the angular frequency, that's 2 pi ft for sure, and phi is the phase, right? So this representation simplifies mathematical operations this helps to simplify operations like differentiation, integration, and convolution in the frequency domain, right? So the real and imaginary parts correspond to cosine and sine components respectively, allowing a compact description of oscillatory behavior in linear systems. So the interpretation is that real part is cosine, imaginary part is sine, right? Just like I said the other time. So of course, we saw that fundamentally somewhere. Where was that? I think when we began to talk about complex numbers. Okay, you can see the real part is cosine. It's not attached with j, and the one attached with j is sine. That's the complex part, the imaginary part. Okay. So then we talk about phasors. Phasors are rotating vectors in the complex plane representing sinusoids. For instance, in electrical engineering, I think there's a bit of just a tiny thing here. We're talking about phasors, right? Yeah, down here. So I can correct this. This is okay. Okay, like I was saying, in electrical engineering. Okay. All right, back here. So in electrical engineering and physics, phasors simplify sinusoidal steady-state analysis by representing sinusoids as rotating vectors in the complex plane. For instance, if you have v of t equals the real part of v naught e raised to power j omega t, where v naught, okay, this also, I can make it, I can write it in LaTeX format. Of course, this is also acceptable in Markdown. It's better to use dollar signs. So you can see the V naught would have changed to proper V naught now. Okay, let me just click down here to get that back. Yeah, so we have all that in order now. Okay, so where V naught is a complex constant encoding amplitude and phase, right? Then we talk about the physical meaning of frequency, amplitude, and phase, right? So frequency measures how fast a waveform oscillates expressed in cycles per second, that's hertz. Its angular counterpart is omega, which is 2 pi f. Now, for the physical interpretations now, we have in acoustics, frequency relates to pitch, how high the sound goes, right? In electromagnetics, frequency defines wave energy, that is E is equal to H multiplied by the frequency. Then we talk about amplitude next. So for amplitude specifies the size of the oscillation. So it tells you how big the oscillation becomes. Physically, in sound waves, amplitude correlates with loudness, right? Okay, I think pitch will be something like sharpness, the sharpness of the sound, while the amplitude, we talk about the loudness of the sound. So in voltage signals, amplitude relates to signal strength, okay? What is the strength of the signal when you talk about voltage signals. And then, so when you convert something from the time domain to frequency domain, you're basically talking about frequency, amplitude, and phase, right? So like we said, in terms of sound, frequency means how sharp the sound is. Amplitude means how loud the sound is. And then we come to the phase, right? So for phase defines the position. Phase defines the position of a waveform relative to a reference point. So you have a reference point. You want to see a waveform, how what the position of a waveform is relative to that reference point you have defined. So a phase shift can alter how waves interact, right? So two waves in phase, same phi, reinforce each other. So if you have two waves, it's more like two people combining energy together. So they can actually become stronger like that. So it's more like you're playing two guitars at the same frequency. The sound will be reinforced, so to speak. On the other hand, two waves out of phase by 180 degrees cancel each other. That's destructive interference like that. So I think that is very demonstrable in water waves. So if you start a ripple at a ripple and 180 degrees after, you cause another wave in the opposite direction. So the two waves will meet and they cancel themselves out, basically, right? So let's talk about some parameter, symbol, and meaning. Of course, that's just a summary of what I've been talking about. So talking about frequency, the symbol is F. It tells us how fast the waveform oscillates, right? You know, so it's more like if it is a sound wave, how fast does the sound travel? That's what you can think of in that regard. And then, of course, if it is yeah, okay, let's leave that. Then amplitude. Amplitude talks about the size of oscillation and it is related to energy or loudness, right? So how loud does the sound get, right? And then we talk about phase. It talks about the relative position of waveform, crucial for interference. Okay, let's go on to talk about sinusoidal superposition. Okay, so talking about sinusoidal superposition, the signal is defined as x of t equals 3. If you have a signal defined as x of t equals 3 cos 2 pi 50t plus 2 cos 2 pi 120t plus pi over 4. So from all of this now, if you have the signal, 50 hertz, the 50 hertz component is the amplitude. So for the 50 hertz component now, so you have a 50 hertz component here, the amplitude is 3. All right, for the 120 hertz component, so the 120 hertz component, the amplitude is 2, and then the phase is pi over 4. Okay, this is also not appearing well, so it's better to put it in dollar signs. Okay, dollar signs. So with this now, you can have the proper, yeah, you can have it appearing correctly. Okay, so for the 120 component, now you see that the amplitude is 2 and the phase is pi over 4. So the total signal will be the sum of all the components. So the total signal you get from here is the sum of all the components. Now, let's see a Python visualization of all the things we've been talking about so that we can see things practically. Of course, to run this in Python, right, we need NumPy for the calculations, and we need Matplotlib to visualize. So you have to run that. So I run this. So import the libraries. Okay. So we run that. So that has been run. So once you see a tick here, it means that cell has been run. So here you see this is empty. So you see a play button, but then if you remove the play button, this place is empty. So that means that we have to run that. So we talk about the phasor representation. So for the phasor representation, so this is how the code goes. You set the amplitude as 1. So you can make it, so you can vary all these values you see here. You can vary them to suit what exactly you may want. So if you have an amplitude of 1 and you have the phase angle to be pi over 4, of course, pi over 4 is coming from numpy. That's why we're doing np.pi over 4, right? You can only get pi from numpy. That is the numpy that we had declared here as np, right? So anywhere you see np, that's numpy, which is a library for numerical Python, right? Okay, so numpy is an array object of arbitrary homogeneous items. Okay, fast mathematical. Okay, that's that. So you have the phase angle, then you have theta. Okay, theta. So now theta is more like the input for the it's more like the angle, right? So it's more like the input. So you have from 0 to 2 pi, that's from 0 to 360 degrees, and you are dividing that in 1000 equal divisions. So the phasor now is defined as the amplitude multiplied by the exponent of 1j multiplied by theta, right? And then the reference vector is a times np times phi. Okay, so that's the reference. And then you come over here where the actual work is being done. Of course, this line 9 is just defining the size of your figure 6 by 6. So you can change it to make it bigger or smaller. Then the actual work is actually happening in line 10. Okay, this line 10 is where the actual thing is happening. So here you have plot plt.plot. Of course, remember we imported matplotlib.pyplot. If you've been following me on data analysis and all of these things, you'll understand that matplotlib is a data visualization tool, so we can use it for plots and things like that. Okay, so anyway you see plt.plot, that's for matplotlib. So for matplotlib now we want to plot the real phasor, just the real phasor against the imaginary phasor, and then we label it as rotating phasor like that. So the x-axis is the real phasor, while the y-axis is the imaginary phasor. And of course, don't forget the phasor has been defined here in line 6 as amplitude A, which is 1, np exponent 1j theta, and the reference vector is in line 7 this way. Okay, so in line 12, you have plot arrow 0, 0. Then you have the real part of the reference vector and the imaginary part of the reference vector also. So the head width is 0.05, head length is 0.1. So you can change these values to see what's happening. Then you can label X label is real, Y label is imaginary, the title is phasor representation, and you want grid, and then you want equal axis for both sides. So if you run this now, it gives you, something like that. So you have the rotating phasor, okay? That's the initial phasor is in red, all right, but then the rotating phasor is the circle. So this initial phasor now begins to circle around, move around like that, and you see what it marks out. Because the amplitude is 1, that's why it goes to 1 at the top and 1 down. So if I change the amplitude to 10, of course it will mean that it will go to 10 up and down. So you can see the values have changed now. 10 up, 10 down. Okay. So let's take it back to 1. So take notes. You see, this is 10 now and 10 down. So, but if I change it to 1 and just control enter, I'm running it. So you see now it changes from -1 to 1. That's the amplitude. So the explanation for that is the red arrow, as you can see, is actually the initial phasor with phase phi, and then the blue circle is the rotating phasor, like if you can see already. Then we can do some sinusoidal decomposition of all of that. And what we're basically doing here is that we have another line space from 0 to 0.05, and we are divided into 1000 equal divisions. And then we have two components now. We have x1 is 3 np. I mean, you can only get cosine from numpy. That's why we're doing np cos 2 pi 50t. That one we saw before. All these ones we had before. These expressions that were declared 3 cos 2 pi 50t, 2 cos 2 pi 120t. So that's what we have here. So you have 3 cos 2 pi 50t and 2 cos 2 pi 120t. Anyway, you see NP, it means that, for instance, cos can only come from numpy, pi can only come from numpy. That's why we're doing all of this. So the total signal is now x1 plus x2. So beyond writing the expression, so we can actually represent the sinusoidal decomposition here. And then the actual plot, like I said here, you have the time, you have the t part, which is what you are dividing now, from 0 to 0.5, and then the x total, which is x1 plus x2. So you are plotting x total against time, and then the color is black for the plot, and the label is total signal. And then you can also break it. So you have plt.plot. So now you are plotting x1 against t, x2 against t. You are splitting them up. So the x1 is with the 50 hertz component, while the label, the x2 is the 120 hertz component, just like we saw in that equation. And then x label is time in seconds, and then y label is the amplitude. And you are plotting, the title is sinusoidal decomposition. So if you run this, by clicking on the play button, or you do control enter, this is exactly what you get now. So you get the total signal now is when you add x1 plus x2, this is what you're getting. All right. So you can see the total signal seems to have higher amplitude compared to either signal at some strategic points, especially where they superimpose. Well, maybe not always. So it depends on if they are in phase. Like you can see, imagine this place now where the 50 hertz components and 120 hertz components, where they are in phase, so to speak. You see that the total signal is stronger, but where they are in opposition, so you see the 50 hertz signal is up, while the 120 hertz component is down. So you see that the phase for the total signal comes down like this. So you can see, I mean, this demonstrates to you how waves can cancel themselves out like that. So explanation, you see the black line is the total signal where you add x1 plus x2 together, just like what we did in line 7 right here. Okay, and then x1 and x2 are, x1 of course is the 50 hertz component, x2 is the 120 hertz component signal, right? So the dashed lines are the individual frequency component, just like we said. Then we can also look at the Euler's formula illustration. So for the Euler's formula illustration, you have theta, you have theta from 0 to 360 degrees divided into 1000 equal components. So for Euler now, Euler is e raised by I theta or j theta in this case. So 1j is what we mean by j theta, right? And then the cos component is np dot cos theta, whatever theta is. Then the sine component is np dot sine theta, right? So then here now you want to do Euler's formula illustration. So you plot the figure 6 by 6. So then you're plotting the real value of the Euler against the imaginary value, and then you're labeling it e raised by j theta circle. All right, and then you're doing another plot. So you're doing theta against the cos components, and you're doing theta against the sine components. So and we have them in blue and orange. Then you just do the labeling. The x label is the real part of e raised power j theta or even theta itself, and then the y part is the imaginary part, and then you plot the title, which is Euler's formula illustration. So if you run this, I press Ctrl Enter and running that now. So you see that here now the circle is the tip of e raised by j theta. So e raised by j theta, so this circle is the tip of it. So as you can see, the blue line, so the cosine and sine curves are real and imaginary parts now. So the blue line is cos theta, while the orange line is sine theta, like that. Okay, so that's Euler formula illustration, where we see that the tip of e raised by j theta. E raised by j theta, that's the one in blue now. Okay, so by way of explanation, and we now have that the circle is tip of each theta. Cosine and sine curves are the real and imaginary parts. Okay, so this, in summary, we see that when we talk about phasor, the representation is amplitude multiplied by e raised power j, the imaginary part, into omega t, angular phase angle times t plus the phase difference, right? Or the phase, right? So the physical meaning, it's a rotating vector made up of amplitude and phase. Then we talk about the sinusoidal decomposition, where you can actually break down what you have in time component into frequency components, and it's a summation of all of that. So you have the total signal as sum of components. And for the Euler's formula, you have e raised by j theta equals cos theta plus j sine theta, and it links complex exponentials with sinusoids. So with this, we come to the end of this second video, talking about the mathematical and physical foundations of spectral analysis. Okay, mathematical and physical foundations of spectral analysis. That is what we have in this regard. So let me know how helpful this video is for you. And if there's something you like when you try out, feel free to let me also know in the comment section, either on Facebook or on YouTube. If you have subscribed to the channel already, thank you very much. If you have not, please go ahead and subscribe, because you have a lot to learn here. All right. You can also take it a step further and hit the notification bell so you can always get alerted each time a new video is released. You can be a member of the channel by clicking on join, and then you see 3 levels of membership, and that it also gives you some special privileges. So feel free and let's interact on this channel like that. All right. So ultimately, don't forget to like, share, comment, so that more people can have access to the great content I have here. Till I come your way again, keep doing maths right. Bye.